What's up everybody? In this tutorial, you are going to code an actor critic agent in a continuous action space. That's right, we're going to go after the continuous mountain car problem using PyTorch. You don't need any prior knowledge, you don't need any experience with PyTorch, reinforcement learning, you just need to be able to follow along. Now, full disclosure, this agent doesn't actually learn to beat the environment for reasons that I'll make clear as we get later in the video. Nevertheless, it's really important to study the continuous actor critic problem because it kind of serves as the basis for more advanced algorithms like PPO and deep deterministic policy gradients, DDPG. So in this video, we're going to go ahead and show all of the strengths and limitations of the algorithm just in the interest of transparency and full disclosure. Let's get to it. So as always, we start with our imports. Now, as I often do, we are going to split this into two separate classes. The first class is going to be a generic deep neural network with two hidden layers with a variable number of outputs based on what we need. And the second class will be the agent class that handles the functionality for learning, choosing actions, as well as instantiating the two networks. Now, in actor critic methods, we are going to use two deep neural networks, one for the actor, which tells the agent what action to choose. In other words, it approximates the policy. And the other network is going to be the critic that tells the agent the value of that policy. These two play off of each other. The critic kind of tells the actor what is good and what is not, and they both sample transitions from the environment to minimize the error in their loss functions, which causes the agent to converge on a semi-optimal policy. As I said earlier, we're not going to beat the environment, but we're going to get an interesting solution nonetheless. So let's start with the generic network first. Now, all PyTorch classes derive from nn.module. That's the base class for PyTorch, and it's what allows us to access the agent's parameters as well as some other interesting functionality. Of course, our initialize function is going to take a learning rate, input dims, the dimensions for the first fully connected layer, dimensions for the second fully connected layer, as well as the number of actions. And we want to call the superconstructor. I forgot the self. So now we want to keep track of all of our parameters. Next, we want to actually construct our network. So as I said, it's going to be a pretty simple deep neural network with two fully connected layers. Since the mountain car problem is only two-dimensional, we really don't have to worry about convolutions, although if you wanted to do a convolutional neural network to parse screen images for, say, Space Invaders or Pong or Breakout, then this would be the place that you would do it. Now, if you're not familiar with it, this verbiage here, this idiom star self input dims, this will unpack a list or a tuple. So this gives us some functionality where if we wanted to extend this to include convolutions, we could, or even not necessarily convolutions, but environments that have multi-dimensional observation vectors. Of course, mountain car only has a single dimension, but nonetheless, let's make it extensible just for giggles. And of course, the second layer is going to be linear as well, and it's going to connect the dimensions for the first fully connected layer to the dimensions of the second fully connected layer. And the final output is another linear function, and that takes FC2 dims as input and outputs and actions. So this will be the basis for our deep neural network for both the actor and the critic. The difference between them is going to be that the actor will have two outputs and the critic will have one. We'll get to that momentarily. The next bit we need is the optimizer, and that is going to be the atom optimizer. And what do we want to optimize? We want to optimize the parameters of this network. That's where we get the self.parameters from. If you may notice that we've never defined this, and that's where this derivation from the nn.module comes in. So deriving this class from the base class nn.module gives us access to self.parameters. And so we're going to optimize the parameters themselves with a learning rate equal to whatever it is that we specify. Next thing we need to worry about is the device we want to run this on. So if you have a GPU, it's a really good idea to use it. If you don't worry, it's not a huge problem. So what we're going to do is say CUDA 0 for the 0th GPU. Of course, if you have more than one, it'll be 0, 1, all the way up to n-1 GPUs that you have. If t.CUDA.is available. So what this will do is make sure you have enough RAM available on the GPU to actually support adding another model. Otherwise, we'll say CPU. If you have more than one GPU, then it would be, say, CUDA 1 or whatever other GPU number you want to use. So if you want to run multiple models on different GPUs, you are more than capable of doing that with PyTorch. And finally, you want to send the entire network to the device. This is a critical step to make sure you're actually computing on whatever device you're specifying. And that is it for the definition of our network. Next, we need to define the forward pass. And this is a little bit interesting because the Actor and Critic do totally different forward passes because they're computing totally different things. And we'll get to the details on that momentarily, but for now, let's go ahead and define the feed forward function. So first thing you want to do is make sure that your state is actually a tensor. In the case of the OpenAI Gym, it's going to come in as a NumPy array, and PyTorch is really particular about the types of data that you pass it. So you want to make sure that you cast it to a PyTorch tensor and specify the D type of tensor.float. And you also want to cast it to the device. This makes sure that it is a CUDA float tensor and not just a float tensor. Those are different things, and it's to make sure that all of the data types of the inputs match up to the data types of the network that we defined up here. So next thing we need to do is go ahead and feed forward that observation, the state, through the first layer of the network and perform a ReLU activation. So that will perform the first feed forward, and next we want to do the next layer, of course. And of course that will just take X as input because we've gone from state, from state to X here, and so now X is the input for the second layer. And the final layer is just going to be the third fully connected layer with no activation. And the reason is that we're going to handle activation later when we choose actions. And when we choose actions, and the reason is that the activation, the range of values that are permissible for the state value function and the actions are totally different. So you don't want to actually activate it here. You just want to feed it forward and handle the activation later. So that is it for the generic network class. It is very straightforward. As you can see, it's pretty simple. So the next thing we need to do is code up our agent class. And this just derives from the base object, and we need its own initializer. And this will take two different learning rates because the two networks, the Actor and the Critic network, have their own learning rate. So you'll have a learning rate for the Actor called alpha, learning rate for the Critic called beta, the input dimensions, the gamma, which, if you're not familiar with it, gamma is the discount factor for future rewards. So the agent takes in when the agent performs a learning step, it calculates the value of the present state as well as the next state, and you want to discount that next state by some amount, and that number ranges between 0 and 1, where 0 makes the agent totally nearsighted, it only considers the current reward it's receiving from the current state transition, and 1 makes it totally farsighted, where it places equal weight on both transitions for this state and the next one. And typically you'll choose something in the 0.9 and above range. So we're going to default n actions to 2 because we already know we're dealing with the mountain car problem. And now keep in mind, don't get confused here. This is the continuous mountain car problem. I just want to specify. But we do need 2 actions, quote unquote 2 actions, because of the way that we will calculate the agent's policy, which I'll get to momentarily. So layer 1 size, layer 2 size, and I have to specify defaults for those. Let's default to, I don't know, 64, something like that. And we need something called the number of outputs, which I will get to in a minute, of course. So let's go ahead and save our parameters. Gamma, we need something called the log probs, and the log probs is going to be used in the calculation of the cost function for the Actor network. This is just the log of the probability of selecting an action. So just to be clear, the actor is the deep neural network estimate of the probability of choosing an action given you're in some state or the policy. So you're dealing with a probability, and when you do the gradient of that quantity, you end up with a log term. And so you need something that gives you the log probabilities, which is this quantity, which we just initialized to none. We'll calculate it momentarily. Next, we need to define our actual actor and critic networks. So the actor is just a generic network with learning rate of alpha, input dims, layer 1 size, and of course layer 2 size, and n actions will just be n actions. Next, we need a critic network, and it will be pretty similar. Of course, there are differences. The differences being that we need to specify the learning rate of beta. We're going to use the same input dimensions and layer 1 and layer 2 size. Ooh, that's a typo. So you could, in principle, specify different sizes for your actor and critic networks. In other words, the number of nodes in the hidden layers. But I haven't experimented with that, and it just seems like an unnecessary hyperparameter to tune. Let's just simplify things and make it nice and straightforward and make them the same. So next point of contention is the number of actions. So of course, for a continuous problem, you really only have one action, but how do you choose an action? You do it through a probability distribution, in this case a normal distribution, and so that normal distribution is characterized by a mean and a standard deviation, two quantities. Hence we have two actions for the actor, in other words two outputs, not really two actions but two outputs for the actor network, and the critic network is tasked with estimating the value function for that particular state. So it only has a single output because you're only computing a number, a real valued number. So we instantiate the two networks, and then we are done with the constructor for the agent. Next, we need a way of choosing actions, and that of course just takes the observation as input. And so the next thing we have to worry about is feeding forward the observation through the network. And recall, for the actor network we have two outputs, so we're going to get a mu and a sigma out, and we get that from passing forward the observation through the actor network. Now, recall that we have simply passed back the value without activating it, and so that sigma could very well be a negative number, and of course a negative standard deviation is a totally meaningless quantity, right? A standard deviation is real valued strictly, so you have to make sure that the standard deviation is real valued, and in particular non-zero, right? It's not a Dirac delta function, it is a normal distribution. So we're just going to exponentiate it with the e to the power of sigma. So that'll give you some some positive quantity. Next up, you want to calculate the probabilities of taking the actions by using the the torch distributions. In this case, a normal distribution modeled by mu and sigma. And so what we're doing here is calculating that normal distribution characterized by mu and sigma. And of course, mu and sigma are the outputs of the neural network for the actor class, and that is what the agent is going to seek to learn. It is going to seek to learn mu and sigma such that we can maximize the agent's reward over time. Next, we want the actual probabilities and an actual action, and so we're going to sample that normal distribution, but we need a shape, right? So you have to know how many things to sample from the normal distribution, and that's given by sample shape, and that's a tensor size self.n outputs. So here n outputs is just 1, and this is what will give us the single sample of a normal distribution characterized by mu and sigma that is a continuous quantity. We haven't bounded it yet, but it is a single continuous quantity from a normal distribution. Next, we need to actually calculate the log probability of that, And this comes into play when we're doing the actual learning for our network. So it's actionprobs.logprob of probs, and we're going to send this to the actor's device. So this gives us the log of that probability, and that's used in calculating the loss function for our deep neural network. And finally, the this quantity is just from the from a normal distribution, and it could have really any bound, right? It could be from plus minus 5, minus 5 to minus 3 or whatever, which are of course meaningless quantities for the mountain car problem. So we want to bound those actions between plus and minus 1, which if you look at the documentation of the continuous mountain car problem is the actual limit of the actions. So to do that, you want to use the tan hyperbolic or tanh of the probabilities. And so this will take whatever number this comes out as and bound it to plus or minus 1. So you end up with a continuous number between plus and minus 1. And then what you want to do is return the action because you've selected it, but you don't want to return a tensor. So this is an actual tensor, and you don't want to return a tensor because the OpenAI gym doesn't take tensors as input for the step function, so you have to actually get the value of the tensor by calling .item function. So now we have figured out how to choose an action. And let me change that to choose action, not choose actions. And finally, we have to come to the learning functionality. So the learning is a temporal difference style, which means that it learns at every time step using the old state and new state action and rewards. This is very similar to Q-learning, and will even have a very similar kind of loss function to Q-learning. But that's kind of really where the similarities end. This is in contrast to policy gradient methods, which is of which actor critic is a subset. But in policy gradient methods, it's Monte Carlo style, where you accumulate memories over the course of the episode and replay those memories and use that to train your network. So in this case, we're training the network every time step off of a single observation. Now, in other variants of actor critic, this is facilitated by a replay memory similar to Q-learning, where you keep track of a whole set of transitions and then randomly sample them to train your network. We're not doing that here. We're just going to use one sample. That's the current transition. But just keep in mind that more advanced algorithms that actually do a better job at solving environments will keep track of a replay memory that it samples over time, that it samples randomly, sorry. So the learning function takes a state, reward, new state, and done flag as input. So of course we need the current state to get its value, the reward, the new state to get its value, and the done flag because the agent doesn't get a reward after entering the terminal state, right? So once you're in the terminal state, you get no further rewards, you're done, right? You collect your prizes and you go home. So you want to have a way of accommodating that, and that is through the done flag that we pass in from the OpenAI gym. With all sorry, I can't talk here. With all PyTorch learning functions, you want to zero out the gradients at the top of your learning function, and the reason is that you don't want the gradients from a previous sample to affect the calculation of the gradients from the current sample, and it also helps with performance. I've forgotten this, and it chugs along after a few iterations. So we have to calculate the value of the current state, we'll say the next state, by passing forward the new state through the Critic network. And we also need the value of the current state by passing that through the Critic network. Keeping with the peculiarities of PyTorch, we need to cast the reward to be a torch tensor. So we'll do that now without pressing the caps lock key. And we want to cast it to tensor, sorry, t.float, and make sure that it's on the device. It doesn't matter if you have actor or critic here, it's just a reference to a particular device. So next you want to calculate the delta, which is the temporal difference loss. You can check out Sutton and Bardo for the explanation of this, but it's basically the reward plus self.gamma times the value of the next state, critic value underscore, times 1 minus the done flag. And so what this does, the 1 minus done, is if the episode is over, done is true. So you have 1 minus int of true, 1 minus 1 is 0. So then it totally discards this term and just has the reward minus the value of the current state minus critic value. And of course, if you're not done, then this is just 1 minus int of false. So 1 minus 0 is 1. Then it's the full expression. So that's how we take into account the fact that we receive no rewards after the end of the episode. So now let's calculate the actual losses. So the actor loss is just negative self.logprobs times delta. For a better explanation of this, you can check out my previous video on actor critic in discrete action spaces. It's the same loss function, and the critic loss is just this delta squared. And so this delta will tell you the difference between the next state and current state, and you use that to guide the evolution of the probabilities in policy space over time with the actor loss, and the critic loss just seeks to minimize that quantity. So the key thing here is that you have the first power of delta, so if it's positive, it'll move the log probs one way. If it's negative, it'll move log probs the other way. And here it is just a delta squared, so it is positive, so it is strictly positive, although it could be 0. And really what you're doing there is trying to minimize this delta between critic value underscore and critic value. So next, we want to sum the two and backpropagate that loss. You cannot say actor loss dot backward and critic loss dot backward. You can only have a single backpropagation step per learning function, so you just have to sum them. Next, actor dot optimizer step. So once you have calculated your gradients and all that stuff, you want to go ahead and run your optimizer. And if you don't do this, it won't learn. I have mistakenly done that. Just typoed it out and wondered why I didn't learn. That was pretty stupid. Okay, so this is it for the continuous actor critic problem. So we have gone ahead and coded up the two relevant classes we need, and they're good. So we're going to go ahead and code up the main function and test this out. Let's do that now. So of course, again, we start with our imports. We're going to need NumPy because we're going to have to do some reshaping of our action. We'll need Gym, of course, from actor critic continuous. We want to import our agent. We'll need my plot learning function. I should just make a video on that one day. It would be pretty quick, easy to do. And if you want to save the output of the renders to an MP4 file, you do from Gym import wrappers. So let's go ahead and get to it. We want to initialize our agent with an alpha of 0.12345. Is that right? I'm looking at my cheat sheet now. 1, 2, 3. I'm just going to copy and paste it. And these learning rates are quite small, and I think I'm missing a 0. And these learning rates are quite small, and it's quite sensitive to perturbations in the inputs of the learning rates. So the beta gets a slightly larger learning rate of 1 by 10 to the minus 4. Input dims is just a list of 2, and this is why we need the tuple or list unpacking in the definition of our deep neural network. And of course, the mountain car environment has only 2 parameters, which is the mountain, the car's position, and velocity. Gamma 0.99, a layer 1 size of 256, and a layer 2 size of 256. So now we make our environment. Mountain car continuous v0. We're going to keep track of a score history so we know that it's learning. A number of episodes, something like 100. So let's iterate over that. and at the top of each, set done to false, score to 0, reset your environment, and then you're ready to play the actual episode. So while not done, you want to select an action from the environment, choose action, that takes the observation. Now, funny thing here is that the action has to be a NumPy array, so let's go ahead and handle that here. NumPy array, and we'll reshape it to a single element. Just a peculiarity of this particular environment. You wouldn't do this in general necessarily. So let's go ahead and take that action. And after you've taken the action, go ahead and learn. Passing in the old state, reward, new state, and done flag. And to make sure that you select an action based on the updated state, set old state equal to new state. Keep track of your score. And at the end of the episode, go ahead and append that to the score history for plotting. And do a print statement to let yourself know that it's running. Episode and print I, and then score %2f %score. When it's all said and done, go ahead and use my handy dandy plot learning function to plot the output, score history, file name, and a window of, say, 20. Whatever. Let's do 20. Whatever. Window of 20 games. Doesn't really matter. So now let's go ahead and head to the terminal and see how many typos I made. 1 second. Alright, so now we're in the terminal. Let's go ahead and see how many typos I made. I forgot an equal sign. Easy fix. Let's run it again. And it's doing something. Local variable action referenced before assignment. Okay. Let us take a look here at the code editor. So that error is on line 49 equals it should be action underscore probs. Okay. Alright, now back to the terminal to see what other typos I have. Alright, it's running. So you can see now that it's running and the score is going down, down, down. So I showed the plot learning function at the beginning of the video, and I'm going to go ahead and spin it in here. Now you see something very, very curious. It actually settles on a reward near 0, and the reason is that if the agent never actually makes it over the hump to get to the goal, then it never actually figures out it can get a reward of 100. And so the best it can possibly do then is try to minimize the negative reward it gets, and it does that by basically kind of sitting at the bottom, exerting minimum actions, rocking back and forth. It's a pretty silly solution, but it is a viable solution, and it kind of goes to show what happens when you don't really carefully design your rewards. Now this is an example of where actor-critic methods go wrong, and the reason this happens is, aside from the fact that it needs to get over that hump in the first place, and it doesn't always do that, but it happens that we get instability if you let it run longer than 100 episodes, because the estimate of the value function is quite unstable. So there are a number of ways of fixing that. Advantage actor critic, asynchronous advantage actor critic, proximal policy optimization, deep deterministic policy gradings, you know, a whole host of algorithms that actually serve to fix actor critic methods and make them significantly better, and indeed they do work quite well when you apply some more finesse to them. But this very simple version does relatively well considering what it is, and actually gets a decent score and an intelligent solution to a actually difficult problem. So I hope this has been helpful. If it was, make sure to share this video. It really helps me to get found. Leave a like, a comment, a question, whatever. I answer all my comments, so leave them down below, and I look forward to seeing you in the next video.